Hello, today I'm excited to talk about a really good eigenvalue eigenvector example. So when we're talking about eigenvalues and eigenvectors, we're talking about a mapping. This is related to a linear transformation that's defined by an n by n matrix, a square matrix. In this case, we're going to be looking at a 2 by 2. So a mapping, we're interested in when a mapping maps something onto itself. So we're going to find out about that. And the example that we look at today has great physical meaning. So here we go. We've got the scenarios. We've got two springs that are connected in parallel, and these springs are loaded. So in order to hold this spring system in static equilibrium, I would have to apply an Fx and an Fy, some Fx and some Fy. So there would be some vector force that's applied to point P in order to keep the spring system in static equilibrium. Now I want you to think about this. What if I were to move that point P a little bit in a delta X and a delta Y? What would happen to that static force? What would happen to it? Well, it's going to tweak too. It's going to change. It's going to change a little bit in Fx. It's going to change a little bit in Fy. So we call these things delta. So the delta here means a very small change. Just we have a delta X and we have a delta Y that we're talking about. And it's going to be related to a delta Fx and a delta Fy, which are changes in that vector force. So I think of it as a tweak. These are very small changes in both displacement and change in force. Okay, very, very small. So what does that is this 2 by 2 matrix. So this is what we're going to be interested in. We're going to be interested in figuring out how to quantify what this 2 by 2 matrix looks like. So the mapping is defined by this 2 by 2. We can call it a stiffness matrix. The mapping relates to displacements in magnitude and direction, displacements, magnitude and direction with a change in force, magnitude and direction. So that's what we're going to be interested in. So let's take an example. I created a numerical example, and we're going to figure out how to get these numbers actually later on. But here's my stiffness matrix, and I'm just going to say, hey, I'm going to move point P 1/1000th of an inch to the right or in the X direction. I'm not going to move P at all in the Y direction. So this is what I'm thinking about. So I take the delta X and the delta Y there, and I multiply it into the stiffness matrix. Really only going to pull a scaled version of that first column. So that's what I get, and then I get the magnitude of that resulting change in force, and I show it there, and then I think about, well, what's the direction of that change in force? Well, it's going to be the inverse tangent of 0.374 or 3724 divided by 0.9281. So it's going to be about 21.8 degrees. Okay, so obviously that change in force is not occurring in the same direction that the thing is displacing, right? So that's an obvious situation, but this is what it is. Okay, let's take a different example. Let's say I'm going to move delta X and delta Y both in 1/1000th of an inch. All right, so I'm going to move 0.001 in delta X. I'm going to put 0.001 inch in delta Y. So I'm going to multiply the matrix, the stiffness matrix, times that. And here's the resulting delta Fx and delta Fy that I get. And then I take the magnitude, and then I can get the direction of the unit vector that way. And I see that the unit vector is in the direction is 50.1 degrees. So you see that they're very close, but they're not perfectly aligned. You know, the displacement, I went in a 45-degree direction for the displacement, and the change in force was actually so the change in force was actually 5.1 degrees more than the displacement direction. So the change in force is nearly the same direction as displacement, but not perfectly aligned. Let's look at this scenario where I'm going to take the displacement direction as 54.46 degrees. And I'm going to displace, in that direction, I'm going to displace 0.002 or 2/1000ths of an inch. So using cosine and sine, I'm able to get the delta x and the delta y that I can put in my column my column vector here, and then multiply that into the stiffness matrix, and I can get my delta fx and I can get my delta fy in this way. And then I go ahead and pull out the magnitude as 1.9787 pound force, and then I unitize, normalize, and get my unit vector. And then look at this. When I take the inverse tangent of 0.8137 divided by 0.5813, I get 54.46. So the change in force direction is perfectly aligned with the displacement direction. And then the ratio of the magnitude of the change in force, 1.9787, divided by the displacement, 0.002 inch or 2/1000ths of an inch, that 989.4 pound force per inch, that's an eigenvalue, and the eigenvector is the cosine of 54.46 and the sine of 54.46. Okay, so you can see it here that as I've drawn it, they are indeed aligned. Okay, so the idea here is that we're going to be trying to put together this matrix, this 2x2 matrix, and the eigenvalues will be stiffnesses and the eigenvalues will be directions where the displacement and change in force aligned. There's going to be two different directions that have this feature. So this is our equation 1. I'm going to show you how to get this matrix. So eigen is a German word that to me means own. So this is a property of the matrix. So the matrix owns that eigenvalue and eigenvector. So let's see if we can figure out how to get that stiffness matrix. So what I did is I started from this image and I tried to get it to scale where I get the point P in terms of this coordinate system, and I get to points A and B according to this coordinate system. So I tried to make it look as though it was to scale. I said the free lengths are 2 inches in each, and I assigned stiffnesses to each. Then easy relations. So L1 is the 2 norm of the vector from A to P, and L2 is the 2 norm of the vector from B to P. And if you think about how to get theta 1, theta 2, you could use delta y over delta x for those. And I like to use the shorthand notation. I'll do this throughout, so get comfortable with this, that the cosine of theta 1 is C1, the cosine of theta 2 is C2, the sine of theta 1 is S1, and the sine of theta 2 is S2. And it's really, for a cosine, it's going to be adjacent over hypotenuse, adjacent over hypotenuse. For sine, it's going to be opposite over hypotenuse, opposite over hypotenuse. So very straightforward geometry here that we're going to use. Okay, so here's what I'm going to do is I'm going to say that the vector force that needs to be applied to the springs is going to be equal to the K1, the stiffness, times L1 minus the free length and the direction of U1. So U1 is a unit vector that is aligned with theta 1. And then U2 similarly is a unit vector that's aligned with theta 2. Okay, so this is the resultant of the 2 spring forces, quite frankly. That's all it is. And then L1, L01, L02 are going to be your free lengths of the unloaded springs. Okay, so putting this into a matrix form, very easily I could have the 2 spring forces in a 2x1 multiplied by a 2x2 matrix to give me that static force, Fx and Fy. What I want to do is think about taking a differential of that. So it's a differential is almost, it's similar to a derivative. You just don't have the with respect to. So I'm going to be looking at a differential force as a vector. So I'm going to have that delta Fx and the delta Fy in the x and y directions. And I'm just basically going to take this relation here and differentiate it to look at the derivatives. Okay, so it's going to be K1 times a delta L1 U1 and a K1 times that force, and then I have a change in direction, a delta U1, and I'm going to do the same thing for the second spring, K2 delta L2 times the U2, and then I'm going to have the force K2 L2 minus L naught 2, that force with a change in direction, a delta U2. Okay, so delta, the U1, remember, is going to be C1 I plus S1 J, and then my delta U1 is going to be the derivative. The derivative of C1 is minus S1. The derivative of S1 is C1, and you're going to have the delta theta 1. So similarly for the second spring, I'm going to have its spring direction and then the change delta 2, the change in direction of the second spring. Same thing, derivative with the delta theta 2. Okay, so this is all pretty straightforward. And then I try to put that back into a matrix form. Basically, I'm going to take and describe what the U1 and the U2 and then the delta U1 and the delta U2. That's what I'm going to do. So that's U1, that's U2 times the change in the first spring length, change in the second spring length, and this is the delta U1 and delta U2 times the change in the force times the delta theta 1 and the force in the second spring times delta theta 2. Now I like to do this. I'd like to I want to get my L's with the theta 1. I want to get the L1 with the delta theta 1. I want to get the L2 with the delta theta 2, because you're going to see why in a moment. So what I do is I introduce these, I call them rho 1, rho 2. So these are ratios of the free length to the length. So when I do that, then I can factor out L1 and L2 over here. So that's going to be useful. All right, so right now I've got my change in force. Let's kind of recap it for a second. I've got my change in force, Fx and Fy. I've got a C1, S1, C2, S2. I've got this matrix here. I'm going to go ahead and diagonalize my K1, K2. My stiffness is there. And then I've got my delta L1, my delta L2. So the change in lengths of the springs here. So 2 by 2, 2 by 2, 2 by 1, change in lengths. And then here I've got my delta U1, delta U2. Okay, and then I've taken the K1 and K2 times that, the 1 minus rho 1, 1 minus rho 2, diagonalize that. And then I've got my L1 delta theta 1 and L2 delta theta 2 as a column vector. So this I'm going to call equation 2. All right, so what I need to do now is I need to figure out how to make this look like a delta x and a delta y, and how to make that look like a delta x and delta y. So that's what we're going to do next. We're going to think about a displacement of that point P. I'm just going to show one leg right now, but that displacement of point P is going to displace some of it in the leg direction, and some the spring direction, and some perpendicular to the spring. Okay, so in the U direction would be in the same direction as the spring. So if I were to take U1 and dot it with this vector, this delta D, then that would be C1, S1 dotted with delta X, delta Y. So that is my change in length of the first spring. Very simply, C1, S1 dotted with delta X, delta Y. So the next one here is where I'm trying to get this displacement here. So I want to think about this direction, which would be delta U1 with respect to theta 1, and that's going to be the minus S1 C1. That's what we did before. It's the derivative of that without the delta theta. So that's why I have it divided by delta theta 1. So if I were to do this, I'm going to get delta X, delta Y dotted with that perpendicular direction, and that's going to be L1 delta theta 1. That's going to be that dimension or that distance right there. And this is going to hold because the angle is like the tangent. You know, for a very small delta theta 1, it's equivalent to the tangent. So that's like opposite over adjacent. So this works very well. And then we're going to rely on that, and we're going to set up two more equations, equation 3 and equation 4, that's going to relate after we repeat it. We're going to repeat it for leg 2, right? So we're going to repeat. This is only shown for leg 1, but we repeat it for leg 2. And you know what? We get a 2 by 2 times a 2 by 1, giving us a change in lengths of the two springs. We're going to have a 2 by 2 times a 2 by 1 that gives us L1 delta theta 1, L2 delta theta 2, right? So we've got really ready to put everything together and get our stiffness matrix. Okay, so my equation 1 is what I'm trying to get. I want to get this 2 by 2. I broke out this equation 2, showed you how I got that from differentiating that static force balance. And then doing that projection, the kinematic projections, I was able to get a relation between delta X, delta Y, and the change in lengths, and delta X, delta Y, and then the change in directions. So now I can take this and substitute it right there. I can take this and substitute it right there. And the end result of this is I'm going to get my stiffness matrix. I'm going to get, you know, that delta Fx, delta Fy is equal to this K times delta X and delta Y. So there's my K. I'm going to have this matrix times this diagonal matrix. And then I'm going to have that matrix over here. And then I'm going to have this matrix right here. And I've got a diagonal matrix right here. And then I'm going to have this matrix right here. Turns out that these are transposes. These are transposes. And since this is diagonal, that's diagonal, this K matrix will be symmetric. How about that? Isn't that interesting? So that is how you get this stiffness matrix, the 2 by 2. And it's good for moving P to different positions and then looking at small displacements from that. You can move it far away from the free lengths. Okay, so here we go. Let's say we're thinking about an eigenvalue problem now, where we're looking at these directions being mapped onto themselves, a scalar multiple of themselves. So that's kind of what I was thinking about here. And thinking about dropping the deltas where I can really kind of focus in on this. So I'm going to be trying to solve this, looking for where they're going to be, where things are going to be aligned. So I bring this over to the other side. And then what I do is look at this as a homogeneous linear equation, quite frankly. And the only way that this would have a non-trivial solution, in other words, where x and y, or delta x, delta y, are not zero, the only way that would happen is if this determinant of that matrix would vanish. So it's a 2 by 2, so it's very straightforward. You have this times this, minus that times that. So I've got that squared away. And then I can sort of collect things where I have a lambda squared. So my lambda is going to be my eigenvalue. And I've got lambda squared, and I have the K1, K11, K22. So that's actually called the trace of the original stiffness matrix minus the trace, sum of the diagonal. And then I'm going to have K11, K22 minus K11, K22 minus K12 times K21. So this is the determinant of the stiffness matrix. So it's pretty straightforward to calculate the coefficients of this polynomial, and you could, quite frankly, easily numerically get the lambda 1, lambda 2. So I think you can do that. And then once you say, let's say, once you have that lambda 1, how do you get the direction of the unit, the associated eigenvector? So here's what I do. So let's say I have lambda 1 is known, and I have the two equations here, but really the two equations are not independent. So I'm going to use the second equation, right? So I'm going to use the bottom equation, and I'm going to solve for y1. So when I solve for y1, I get this relation here. I could temporarily set x1 equal to 1, and then I could get my y1, and then I could normalize it. So this is how I get the direction, the eigenvector that goes with the particular eigenvalue of lambda 1. Okay, so here's the result of it. And we get that 2 by 2 matrix that I showed you earlier. So these elements do have units of pound force per inch. There's my lambda 1. There's my lambda 2. Here's my eigenvector for the first one, V1. So that's the 54.46 that we had a preview of early in the discussion. And the other eigenvector, V2, I've shown in red. So that's actually a negative 35.54 degrees. And it's interesting that, well, it's not interesting. It's a fact that these eigenvectors will be perpendicular. So that's a very nice feature. And then the lambda 2 that goes with it is 451.9 pound per inch. Okay. All right. So here's how I sort of calculated this. So I showed you this already, where I had my positions. I had my free lengths squared away. I have my stiffnesses. I did my L1, L2, and these are just the two norms of the delta x, delta y. I got my C1, S1, C2, S2 from the projections I showed you earlier. And then remember that my K matrix here from equation 5, I dealt with these transposed matrix. This matrix I called J, and then this matrix I called JP or J prime. And there's my KI right here. And here's my KI row right here. And there's how I calculated my K. My K is J times KI times J transpose plus JP times KI row times JP prime, right? And then I kind of set it up where I've got my K1, K11, K12, K21, K22. So I'd set it up like that so that I could very easily put together my my coefficients, the delta, the determinant of the 2 by 2 minus the trace, and then plus 1. Then I could get my lambdas. So I got my lambdas, put those out. And then this right here is what I was referring to earlier, where I could temporarily set x1 to be 1, and then solve for y1 using the lambda 1, the first lambda, and then I get my eigenvector that way, but I want to normalize it so that I get that the nice normalized cosine of 54.46 degrees, etc. sine, and it gives me the angle when I do the tan 2 of that. Repeat that for the second one. And then I wanted to see what MATLAB would give me and how you can use the Eig function. So I give Eig, I give it the K matrix, and then it's going to give me the values. No, the V is going to be the vector, the vectors, eigenvectors, and then D is going to be a diagonal matrix with the eigenvalues in that. So eigenvectors and then eigenvalues. Okay, so I run that, and it's interesting what I get. So I print out my J, print out my lambdas, J and K, print out my lambdas. Here's my eigen, 54.46 degrees. Here's my eigen 2, eigenvector 2, the minus 35.54. And then if you look at what MATLAB's function gives you, it actually gave me, well, first of all, it swapped the eigenvalues. So it gave me the second one first. That's not a big deal. And what goes with that, it was 8137 and 5812, but it negated it. It gave it to me in the 180 degrees off. And then the second one, it also gave it to me in 180 degrees off. So, but again, the angle between the two, they're perpendicular. But the x's, you could put a minus sign for maybe a mu. That's what they've done. They flipped the direction. Not only did they swap the eigenvalues on me, but they also swapped the direction of both eigenvectors. Okay, so here we go. Just kind of wrapping this up. So I've got, the matrix. I showed you the two eigenvalues. I've shown you the two eigenvectors, and you note that the matrix is symmetric. I mentioned that before. And if you kind of look at what's happening with our V1, however I do it with the delta, some displacement scaled that V1, it's going to be the delta F that you get is going to be lambda 1 times that delta D, whatever that magnitude is. It's going to be in the same direction. Similarly, for the second eigenvalue and its eigenvector, similarly, if I were to just do a delta y is equal to 0, that's going to pull out that first column, which is what I did in the first example I gave you. And then if I were to swap that, if I were to say delta x is 0, that would only pull out the second column. Okay, and then remember in these examples that my free links were 2. Okay, so today we discussed a mapping. We discussed a mapping where something was mapped onto itself. That's an eigenvalue, eigenvector pair. And then we did a great physical example of this. I hope you thoroughly enjoyed it.